Hello everyone, this is Deepika Sheel and today we are doing the next lecture, which is lecture number 5. And uh, previously we were doing sources of water, and in that only we are doing the next part in the sources of water. We can say it's part 2. So the lecture name is Groundwater Properties, and in which we will be studying uh, porosity, permeability, hydraulic conductivity, and Darcy's law. So, uh, let me give you my introduction. I am currently pursuing my M.Tech from IIT Kanpur, and I am doing it in civil engineering, specialization in environmental engineering. So, and we are here to make GATE 2027 more uh, uh, freely available for everyone to study. So, my motto is to provide good quality lectures for you all. So, let's begin. So, we have, yeah. So, till now, what did we learn? So, till previous lecture, we have learned that what's the surface water, and let me change the color, and what's groundwater. We have studied rainwater, and then how the groundwater was developed. We have done the zone of aeration, we have done the capillary fringe, we have done water table, and then we have also discussed about the zone of saturation. So this is how we worked. Now in next, by the end of today's lecture, we will be able to understand things like what's porosity, what's void ratio, what's permeability, what is hydraulic conductivity, and what factors affect the hydraulic permeability. Then that means we'll be discussing what's hydraulic permeability also, and then what's Darcy's law, right? And then we will be discussing a numerical as well. And yeah, that's how we will be conducting today's lecture, and we'll be finishing it. So let's continue. Now, can you see these two pictures? So we have one side we have sand, and other side we have clay. So see what questions I have found. Can water move through every type of soil? That means there are type of soils like sand, clay, we have silt. So I have shown you two examples here, sand and clay. So just think from your experience, like, can water flow from sand easily? Can it flow easily from the clay? Clay is the one which we use for making the uh, art crafts and all, right? Okay, now we know which will allow water to pass. I think both will allow water to pass, but some will allow it faster, some will allow it in a slower extent. So next question is, which one allows water move faster? Yeah, so yeah, so which one allows water to move faster? So it will be answered in the later uh, video. So this was so yeah, okay. So and the next question is that which one allows water to move faster? Will it move fast in sand or will it move fast in clay? That will be answered with the term which is called porosity and there is one more term which is called permeability. So we will be studying next, which is porosity. So what's porosity? Let's understand it with the example of sponge. We all know what sponge. Okay, so there is some empty space in that sponge, and that how much the empty space there in that sponge, we call it as porosity. The voids, okay, empty space are also known as void. So the ratio of empty space to the total volume of the sponge, we will be calling it as porosity. And in the terms of sand also, sand is sand or clay or in general soil is also having voids, right? So in those in the soil, those voids, volume of the voids divided by the total volume of the soil that we are considering, will be known as the porosity. So that's the porosity. So here we can see that in gravel, so we know that there are three, we can divide it into 3 or 4 types of soils, right? There is gravel, there is sand, and there is silt, and there is clay. Silt and clay they act almost as the same, so I am considering only clay for that. So gravel is what? Gravel is the larger particle, right? So there will be lot of pores here. So this is soil particle and this is pore. That blue colored water is the pore, and in that water is there. So it has very large pores and it has high permeability. Permeability also I will explain what's that, but for now porosity we have to see. And then also you can see in medium sized particles, that's for sand. So there is medium pores, and there is moderate permeability, and there is moderate water retention. Okay, for this, for gravels there is less water retention. That means if water gets away to leave this gravel, it will leave very easily. Water will not stay inside that, so it's less water retention. Okay, but in sand there is moderate water retention. That means water will stay for some time. So I mean water will stay in the sand for larger amount of time. And then we come to clay. Clay is having very small particles, right? So uh, very small particles, and there is very small pore size also, and it has very low permeability. We'll be discussing what's permeability. And then because of low permeability, the water is not allowed to pass very easily, so water retention is very good in clay. So this is what porosity is. So let's move to the next slide. Yeah, so I'll explain you the porosity formula as well. So porosity is nothing but uh, volume of void divided by volume, I can say total volume. Okay, and the void can also have some water also. So voids can, volume of voids can also be written as volume of water plus volume of air. That's what the void is, divided by total volume. We can also denote porosity as N, and volume of void as VV, and total volume as V. So both above in the numerator and in the denominator, both have volumes only. So there is no unit, it's a ratio. And we can just say express it into the percentage. Like the voids are 30% of the total volume. So this is what porosity is. So yeah. Next is porosity versus permeability. Now we'll understand what's permeability. So porosity is the amount of void right? How much the void is there. But permeability is ease of water flow, ease of water flow. That means how easily the water can flow into the soil. Okay, and porosity is the storage, right? Like we how much water we can store in the soil, just like sponge. If the sponge is fully like filled with water, after that it like the water will start leaking from the sponge. So that's the uh, capacity of sponge to retain the water. So that's what the storage is. That much only the water can be stored in the sponge. Similarly, that much water only can be stored into the sand. So it works as storage, but permeability tells about the movement. How much water is moving faster than in different types of soils. And then it's dimensionless, and then it depends on the soil structure. Now we'll be seeing permeability exactly. So permeability is how faster it moves from the soil, one place to other. So if it moves faster, it is more permeable, and if it moves in a very slow manner, then it's less permeable. Okay. So for example, clay. In clay, the we all know that for clay the permeability is very less, but there is a catch. For clay, porosity is too much. Porosity is high, but permeability is low. So I can say that for clay, porosity is very high, but permeability is very low. Why? Because clay has very small pores, and there is a large number of pores. So if we include that, so clay has very high amount of porosity, but the pores are not interconnected. Permeability is when the water, when the pores in the structure or the medium is connected, then only water will be able to pass, right? See, you can see the pores are connected everywhere, so the water has way to go in every place. So these are connected pores, but in clay the pores are not connected very properly. So in clay the water will retain in between the layers. Okay, so clay has high porosity, but it has less permeability. So permeability is simply, we can say, it's the interconnection of pores. So if pores are connected very properly, the permeability is more. If pores are not connected, then the permeability is very less. And I can tell you one more example of opposite, that's granite. And that too, it's cracked granite. So in cracked granite, what happens? That there will be crack. Actually, granite is very dense, right? So there's almost no porosity. So porosity will be very low. But if it's cracked, permeability will be very high. So permeability will be very high. So these two are opposite of each other. But in sand, the porosity and permeability is actually good, moderate, right? So this is how there is a difference between permeability and porosity. Permeability shows the storage, porosity shows the storage, permeability shows the how much water can flow easily. So that's what the difference between these two. Now we will also discuss the factors affecting grain size, permeability, factors affecting permeability. So what's that? Like grain size. First is grain size. So we have just now discussed, if the grain size is bigger, pores will be bigger. Pores will be bigger, there will be higher chances for more interconnection, then permeability will increase. So if grain size is more, then permeability is more. Void ratio. If void ratio is also good, then there can be the chance that permeability is more. It can be low also, depends on the type of soil, right? Degree of saturation. Yeah, if the water is already like filled everywhere, if saturation is more, permeability will be less. Shape of particles depends, if it's flaky, if it's angular, so with that also permeability uh, is affecting. And water temperature. Temperature, higher the temperature, higher will be the flow. So if we increase the temperature, and if we are using it for clay only, then also the permeability will increase. So that's how these are the factors which affect the permeability. Okay. Now next is, now let's move on to hydraulic conductivity. So what's hydraulic conductivity? So it's the how much, what is the rate of flow through the sand. That's what we call as hydraulic conductivity. Okay. So see, for here, for that we have already made one diagram. This is a, let's see, this is, let's say this is a transparent sand medium. Okay. So in which this is the inlet, this one is the inlet, and mm, so this one is the inlet. Yeah, this is the inlet and this is the outlet. Okay. And the inlet water level is at a head H, and the outlet water level we are taking it into the center of the sand. So uh, what we are seeing, what's the hydraulic conductivity, that what's the flow rate of the water, how fast the water comes into this tank, the next tank, lower tank. So hydraulic conductivity is all, like given by Darcy's law that we are going to discuss. So this is the experimental setup what Darcy has done. First of the like key points, let's see here what's the key point, that we need to ensure for calculating the hydraulic conductivity, we need to ensure the constant head. That means if the water level becomes low, we need to fill the water level always at this point, because we have to have constant head. And then water flows through the soil or sand in the pipe due to head difference. What happens? Because there is a head difference, higher head to this, there is a head difference, this is H. Okay. Due to this head difference, the water flows from high head to low head. That we already know, that water flows from a higher head to lower head. So this is why water flows from here. And then this conductivity K depends on soil property, and it's calculated using Darcy's law. So this is what Darcy's law is. So that we will be discussing next. Yeah. And hydraulic conductivity is given by K, simply how fast the water moves. Okay. So for every material we have, like for gravel, the conductivity is very high, water will flow very faster. For sand, conductivity is medium. For silt, conductivity is low, and for clay, conductivity is very low. Okay. Yeah, that's how hydraulic conductivity works. Now we'll be studying the law behind calculating the conductivity. So the question is, why do engineers calculate groundwater flow? I mean, how engineers calculate the groundwater flow? So why we know, right? We need to have like how much flow rate will be there for water, and we need to calculate what will be the level of energy we have to put for the extraction of water. So behind that, what will be the cost for the for providing that energy. So if we know the flow rate, and if we know how fast the water can come from ground to us, then we have the actual idea that how much energy we need. So that's why we have to calculate the groundwater flow. But how to calculate the groundwater flow? That comes with the answer of Darcy's law. So what's Darcy's law? So Darcy has set up this experiment, and it has given that uh, the formula is Q is equal to KIA, where K is the hydraulic conductivity and Q is the flow rate. What will be the flow rate? This is calculated by, this is what flow rate is. So this is how we are calculating how much water is flowing through. K is the conductivity. Conductivity will be the value. It will already be given, and it depends on the material that we have already seen. I is the hydraulic gradient that we will know what is that, and A is the cross sectional area. So water is passing through this cross section, right? So this is the cross sectional area. So this will be putting, this is the cross sectional area of sand. So bigger the cross sectional area, more water can flow, right? So that is the case. And I is the hydraulic gradient. More the hydraulic gradient, more water will uh, more faster the water will flow, and K is the conductivity. More is the conductivity, more it will flow, right? So this is how things work here. Now, so the Darcy's law says that the flow rate is directly proportional to the hydraulic conductivity and the area, cross sectional area, right? And we need to remove the directly proportional sign, so we put it equal to Ki A. K is the constant, and this constant is known as hydraulic conductivity. All right, so this is how the Darcy law is calculated, and from this we can calculate hydraulic conductivity. If we know the flow rate, in most of the questions flow rate will be given and they will be asking us to calculate hydraulic conductivity. So we'll calculate it by Q upon IA, and I is what? I is hydraulic gradient. Now what's hydraulic gradient? Right. So hydraulic gradient is I. It is the difference of head per unit length. So in this diagram, you can see the length is this much, and in this much length, the water head changed this much. So hydraulic gradient is how much head is dropping per unit length. So in L length, H head was dropped. So that's the gradient. Gradient is H upon L, the amount of head drop per unit length. So that's what hydraulic gradient is. So I is H upon L. Head loss is also in meter, L is also in meter, so it's unitless. And the discharge, we already know, discharge is in units of meter cube per second, right? So if we put meter cube per second, and hydraulic conductivity has no unit and area has unit of meter square, so it comes as conductivity is m upon s, meter per second. Meter per second is what? It's the unit of velocity. So conductivity is nothing but the velocity of water, how fast it's flowing. So that's what Darcy's law is, and we have understand this. Yeah, and let's have some few conditions for Darcy's law. So the condition number 1 is the flow should be laminar. If there is any chances of turbulent flow, it will not work. And soil should be fully saturated. That's also a condition. The medium of soil should be homogeneous, and there should be constant temperature. In these conditions only the Darcy's law work. If any of the condition is not following, then the Darcy's law will not give the appropriate answers. So this is how Darcy's law works, and with that we come to an end, and we come to one example, and which shows that we have given the hydraulic conductivity, we have given cross-sectional area, we have given hydraulic head at a point A, and we have given hydraulic head at point B, and we have given distance. So this is HA, this is HB, and if we I is what? I is change in head. per length. So change is 15 minus 10 upon length is 20. So it's nothing but 5 upon 20, and that means it's 1 upon 4. Okay, so now we have K is 0.002 meter per second area, and I is also there, and we need to calculate Q, discharge. So can we calculate? Let's see. We have K, that's 0.002 meter per second, right? Area is 5 meter square, and we just now calculated I, that's 1 by 4. 1 by 4. Can we calculate Q? Yeah, we know Darcy's law, that works. KIA, K is 0.002 into I is 1 by 4 into area is 5 meter square. So if we calculate it, we get discharge as 2.5 into 10 to the power minus 3 meter cube per second. That's the answer. So yeah. So with this, we come to an end of this lecture. We studied the porosity, we studied permeability, we studied hydraulic conductivity, we got to know what's Darcy's law, we saw one numerical. So this is how we are coming to an end. And in next lecture, we'll be seeing what's specific yield, what's specific retention, what's aquifer, what's aqueduct, what's aquiclude, what's aquifuge. So next lecture will be very interesting. I hope you guys got something new to know with this lecture, and I hope you join for the next lecture as well. Thank you everyone.